I went through the online homework for both chapters that we learned, and I've done all of the problems. I
Yeah.
just am still not like just like grasping the overall, like I don't know if I need more problems or if I should just keep doing the same ones over and over again. Does that make
Ye
sense?
yeah, kind of, so what is it like that you're I'll do better if you give me, like, a little bit of a specific, right? So, like, is there
Okay.
for ex yeah, go ahead.
So just like for an example, like when we're doing retrosynthesis, I can like um I know all of the reagents. I just don't know like this kind of sounds silly, but I can't like put a reagent to a actual reaction, but I know what it's supposed to look like. And then when I get to like naming them, I don't really understand.
Yeah, so, like, you mean for, like, in this example, if we were trying to make this, like, how to kind of move backwards through some of this stuff?
Yeah, and sometimes I find it easier to move forwards rather than
Yeah.
backwards. I don't know if that like
Oh,
is
no,
wrong.
it's so funny. So many people say the same thing. I say the same thing, and I know the professors are like, "Oh, you gotta move backwards." I do understand, like, you do have to kind of move backwards a little bit to kind of see where you're going. But I also personally, I usually try to work from both directions at the same time, to try to
Yeah.
get somewhere, and a lot of it's kind of trial and error, which is a little can be a little challenging, and a little frustrating for sure. But it is like a puzzle, and definitely like do not try attempt to do all these reactions like from memory until you're on the exam. Like until you are literally taking the exam, just keep your reaction summary right next to you, handy, easy to see. And the moment you get stuck, don't try to like figure it out and suss it out. Like just refresh your memory. You got to start creating that pathway, right? Of like, you don't want to struggle too much because then your brain's going to remember the struggle more than it is just like the answer. So like if you start to feel like you're like, "Oh crap, how does this what is it that makes this again or how does this work again?" Like just quickly refer to your like, you can call this like a little cheat sheet, right? But your reactions and just like help yourself figure it out that way because unfortunately the only way to learn this and the only way to get good at it is by practicing it over and over and over and over and over and over and over again. And that's why you they want you to practice 600 problems in 6 weeks now for this. 6 weeks, that's 100 problems a week. You're looking at what's that, 13 problems, 15 problems a day or something like that. 15 problems a day. So, if you're not practicing at least 15 problems a day, you're doing yourself a disservice, right? So, um, we can go through like there's just so many different synthesis problems. So I want to be able to like address what you feel like you're having trouble with. So is there maybe like is it like synthons are a really great way to like practice. Oops, synthons right here is a really great way to practice like seeing what's gonna work and what's not, right? How are you feeling about that? Like, are you trying to do synthons? I think usually the first exam or at least in my class, she like asked for the synthons and then the synthetic equivalents. Um, specifically. But it's a really great pattern to be able to like start to do synthesis. How are you feeling about
Yeah.
those?
Synthons I actually do pretty well in.
Awesome.
Uh that isn't like as hard for me. I just like went through it myself and did it pretty well, but I would say just like any example of retrosynthesis would be helpful rather than no example.
Yeah, of course. Yeah, yeah. Okay, so let me see if I go to the practice site, which is where practice site. I'm just gonna put some. And any of you, either Sandra or Ariel, have any specific requests by chance while I'm on here?
Not me. No, not anything specific. Just any help that I can get at this point.
For sure, for sure, for sure. Okay, so let me just pull up this. Let me find a blank page. Here's one. Do, do, do. Good. And page. So all right, I'm gonna put on here. Sometimes it takes just a minute to sync. Do. Okay. And then I'm just gonna put a couple on here while it's taking a minute to think. Okay. Fair enough. Sometimes it takes a minute. I'm shocked it's not loading yet, but I guess what I'll do is I'll just write it out. Okay. It's not loading. Why isn't it loading? How annoying. Okay. As soon as I start writing it, it'll then start loading. Okay, so it's asking, whoops. Okay. So this is the structure. And then we have H new, NaOMe, BHF3 CHM, and then 4 is OH, hydrogen peroxide. Okay, so it's asking us to make the, like, what would be our final, give the major organic product of the final product of this reaction sequence and make sure that you can work out the products for each individual step. Pay attention to your stereochemistry. So with MBS H new, which do you guys remember what H new is?
Light.
Yeah, light energy, exactly. So what does reaction number 1 do?
Gives us a BR off of the most substituted carbon.
Yeah, exactly. So we redraw this and we put a BR on the most substituted carbon, right? I'm assuming you guys know what the most substituted carbon is. Is that a fair assumption, or do you guys need me to explain why this carbon is the most substituted?
I understand.
Yeah,
Okay.
I understand too.
Perfect. Okay, awesome. So cool. So we've done 1. Okay, what's number 2? That's Na plus and OMe minus. So those are ions. Na and OMe. What's the next step do? And it's a good habit to write down your reactions. So N A O M E. Okay. So what's the next one do? Is this elimination or substitution?
Is it elimination?
Yeah, exactly. Yep. Do you remember why it's elimination, or are you just guessing? Fair either way.
Is it because the BR is a leaving group, so it leaves?
It is a leaving group, but it could be a leaving group in SM2 as well, remember?
Mhm.
It needs both substitution and elimination need some leaving group, right? So
Mhm.
in an SN reaction, it would be substituted, right? And in an elimination reaction, EA reaction, it would just be eliminated with a hydrogen. And we would get
Okay.
HBr. So so do y'all remember the difference between what kind of solvent? Do you remember like why the solvent matters? The solvent is these, right? 1, 2, 3, 4. Those are the solvents. So what was it about the solvents that helped determine, let's say, E1 from E2 or SM1 from SM2?
I know it has like something to do with like if it's in the wrong solvent, the solvent will just react with each other rather than something like that. I don't really know.
No, that's okay. That's why we're here, right? So does protic or aprotic ring a bell?
Yes. Yeah, I had it on the tip of my tongue, but I couldn't remember what it was.
Yeah, no, it's all good. It's all good. What is the difference between protic and aprotic?
I believe if I remember, I think protic is for SN1, or am I getting that? Hold on.
You
I
are
can't really
correct.
remember.
No, you are correct. Yes.
Okay.
Protic is SM1. What's the difference between protic and aprotic though? Like how do you tell the difference between protic or aprotic?
Um, I forgot.
That's okay. That's all right. So I'm gonna give you a hint. Does this help ring a bell? What is a proton in terms of, besides like a positive charge, right? But in terms of like the atoms, the elements that we're using, what do we use as a proton? Can you also see my screen?
Yeah.
Yeah.
So a proton is our hydrogen, right? It carries the positive charge. Does that ring a bell? Hydrogen. So
Yeah.
if you, so a protic solvent has some sort of hydrogen that is going to be reacting in the mechanism, right? So now the difference here is that you are going, it's not, if you have I mean, in this case, right? But if you have a hydrogen that's connected to a carbon, is that going to react? Is that going to, um, is that hydrogen going to be used in the reaction?
No.
No. Wait.
Right.
Okay.
If you have a hydrogen that's connected to an oxygen or a nitrogen, will one of those hydrogens react in the reaction?
Yes.
Yes. Why? Why will a proton, aka a hydrogen, interact in this reaction with an oxygen or a nitrogen, but not with a carbon?
Because of where they are on the periodic table.
Yeah, what's that mean though? What does the periodic table have to do with it? Yeah, yeah.
Electronegativity.
Yes, exactly, exactly. what about electronegativity is the difference between these two subsets here?
Wait, can you
Well,
repeat the question?
yeah, what about electronegativity is the difference between these two subsets? Let's call this subset 1 with O and N, and let's call this subset 2 with C. What about electronegativity makes them different?
Oxygen is more electronegative than carbon, meaning it wants a proton more.
Wants electrons more for sure. It's more electronegative, right? Which means that it carries a lot more electrons with it. But the biggest thing to remember is that carbon and hydrogen are basically equal when it comes to electronegativity. So there's no polarity. Do you guys remember dipole? Do you remember dipole moments?
Yeah.
Yeah. So what is it that makes a dipole moment happen?
Is that the same thing as like dipole forces?
Yes, you have to have two dipoles in order to have a dipole force, right? But what is an actual dipole? Partial charges,
Yeah.
right? Partial positive, partial negative. That's what makes it polar. That's what makes it dipole, right? So we have this partial positive, partial negative on this molecule, right? So because oxygen is more electronegative, it hogs the electrons. Do you guys remember molecular orbitals? You guys remember that? So hydrogen has the sigma bond, and oxygen, that should actually be more like this. There we go. And oxygen with the sigma bond, right? But we have this like greater concentration of electron cloud on the oxygen side, right? Because oxygen is more electronegative, right? Do you guys remember this? So that's what creates that dipole moment. So we have this partial positive and partial negative because the electrons are more condensed on this side, right? So, and I'm going back and explaining all of this concept for you because this is very important to be able to move forward, right? So you have to be able to decide if something is protic or aprotic, right? And so in order to decide if something's protic or aprotic, we see if there's a hydrogen that's going to be involved in the reaction, right? Because remember, Lewis acid and Lewis base or Bronsted acid, Bronsted base, right? But the acid base reactions are the most important when it comes to organic chemistry reactions, right? And so when we are having an exchange of electrons, which is Lewis acid, Lewis base, or an exchange of protons, which is Bronsted acid, Bronsted base. Did I get that backwards? I don't think I did. That's what the reaction is, right? That's what any reaction is going to be. It's either it's this exchange of energy in some way where we're reducing the energy of electrons via bonds, right? So to go back a little bit here, right? So a protic solvent is going to have a hydrogen, not that one, is going to have a hydrogen that will interact in that, in a bond, right? And so if you see a solvent that has, like for example, this one, right? Do you guys see in number 2 here, is this protic or aprotic? Do you guys see a hydrogen that would interact in the reaction?
No.
So that means it's
Aprotic.
yes, exactly. So if it's aprotic, then there's 2 out of 4 possible reactions when it comes to substitution or elimination. Do you guys remember what number those 2 are? Are they 1 or 2? Right? Because remember, SN1 and E1 are similar in their solvents, and SN2 and E2 are similar in the solvents. So if it's aprotic, what do you think it's going to be? A 1 or a 2?
2.
Yes, exactly. So this is going to be either SN2 or E2. Now, how do we tell the difference between SN2 or E2?
E2s, I know they have negatively charged bases. I don't know if that is that what you're looking for?
Um, yeah, like again, the solvent does matter. And it's definitely a great plan of attack to look at. But something that I do to help narrow it down a little bit is I look at the degree to which the either um okay, let me back up 1 second. If it is SN2 or E2, are we going to have a carbocation or is it a concerted reaction? Because SN1 and E1 are either, right, concerted or carbocation, and I'm saying either because they are one of those, but I want you guys to tell me. And then SN2 and E2 are either, right? So they're both the same. So SN2 and E2 are both blank, and SN1 and E1 are both blank. Which ones are concerted and which ones have carbocation intermediates? Do you guys remember?
I think substitution has carbocation intermediates and elimination doesn't.
Great guess. Again, it doesn't have to do with substitution or elimination. They both have both. It actually has to do with if it's 1 or 2. So SN1 and E1 are both blank, right? And SN2 and E2 are both blank. So SN1 and E1 are both carbocation intermediates, right? So you have some sort of carbocation intermediate where you most likely will have a rearrangement. Do you guys remember that part?
Kind of, yeah.
The carbocation intermediates, yeah. So those were let me just pull up OChem real quick. Okay. These are from past past messy. This is E2. Let's see. SN1, right? So SN1, we see the bromine is a leaving group. We have a carbocation intermediate. Then we have an alkyl shift, also known as a methyl shift, so that we can have a more stable cation. And that's when our OTOH interacts with this cation. And that's how we end up with this, right? So this is a typical SN1 reaction where we have that carbocation, right? And you would see that similarly with E2s in different ways, right? So this is what I'm talking about with that carbocation shift, right? Or with the carbocation intermediate, right? So SN2 and E2 are both concerted. Do you guys remember what concerted is? What a concerted reaction is?
It rings a bell, but I don't remember what it is though.
Yeah, so a concerted reaction means that it happens all at the same time. So there's no intermediates. And so a lot of times we have that backside attack stuff. And this is a good example of it right here. So a concerted reaction is where as the bonds are breaking, they're also being made, right? So there's no intermediates at all. It literally shifts from one to the other in one step versus those intermediates where there's multiple steps to it, right? So this is a concerted reaction. So as the OT butyl comes in, right, and then we have this in phase of our molecular of our atomic orbitals, right? It comes in And these electrons are pushed off onto bromine, because bromine is a good leaving group because it is a stable anion, right? Which means it's happy to be on its own with its electrons and a negative charge. It's happy to do that, right? And so at the same time that is being broken off as these are coming in, and that's where we have this Walden inversions where we're pushing forward our substituents, right? And so in this case, we don't have Walden inversion because these are all H's, and so there's no difference. We wouldn't notice a difference. But if there were other substituents on there, we would, right? But so this is that this is that idea of concerted reaction, right? Excuse me, right here, where we're having that incoming group and the leaving group happening at the same time, right? So in this case, because this is a concerted reaction, do y'all remember what kind of and this is a concerted reaction, which means that also, so what we're doing by doing this step here is we're putting on a leaving group so that we can add things to it down the road, right? Because we have to have some sort of leaving group, some sort of place to be able to make new bonds to, right? So we've added this bromine here to create a good leaving group. And then, so it's a concerted reaction. So do you guys remember what type of carbons SN2 will react with versus E2? And what I mean when I say that is allylic versus first degree versus second degree versus third degree. Do you guys remember? The SN2 and E2 are very different. So do you guys remember? So if this is our leaving group, then that means that this is the carbon that's going to be interacted with. Do you guys remember what the difference is with all of these?
Are you talking about like 1', 2', 3'?
Yep, first degree, second degree, third degree, yep.
Yeah. So it's gonna be a 3' carbon.
Yep, this is a 3' carbon, that is correct. So what will interact, like, does that precede E2 or SN2?
I'm gonna say SN2. Or maybe E2 because it's so bulky and there's so much stuff around that it needs to leave like as something's coming in.
I like where you're going with this for sure. This wouldn't be considered a bulky base, although yes, you're right, there is steric hindrance here. So if that's what you mean by bulky, there is a lot of steric hindrance on this molecule. Yeah, that's okay. I just want to make sure that I know what you're talking about so I know how to properly answer you. That's the only reason why I'm clarifying. So yes, you're right. There is a lot of steric hindrance on this molecule here. And so SN2 reactions will not proceed with third degree because there is so much steric hindrance, right? So that is correct. Bulky, right? There's too much stuff in the way. That's really what that means, right? So it won't be SN2, it will be E2. And just as a quick reminder of the type of carbons that will be interacted with, right? SN2 prefers allylic or methyl. And then it is first degree and then second degree, and it will not interact with third degree, versus E2 prefers third degree and then second degree and then first degree. So I will say that the only time that this approach isn't necessarily helpful is when you have these second degrees, because it can kind of, here's the other thing to it, they can kind of go both ways. And so they can happen at the same time. So a lot of the times what they're asking for is like, what's going to happen the fastest? What's going to be the most likely to happen the most, AKA the fastest, because the faster a reaction happens, the more of those reactions will happen, right? And so that's not to say that like SN2 and E2 can't happen at the same time, but we're trying to figure out what's going to happen the most, right? And so, okay, so in this reaction, now we figured out that it's an elimination reaction. And we are eliminating what we said. We're eliminating the bromine. And as you guys can see, my notes get very messy because I get very interactive with my my stuff. So I do try to erase it as I go too, so that way it's like a little bit more clear, right? But Okay, so we've decided that our bromine is the leaving group. So what else has to leave with the bromine? What else has to leave with the bromine? So if it's elimination, okay, let me ask you this. If it's elimination, what does that mean that we're making?
A double bond.
Yes, exactly. So what else has to leave with the bromine so that we can make a double bond?
A hydrogen or a bond?
Yeah. And I guess maybe leaving is a bad way to say it, and I apologize. So yeah, so we have to use the hydrogen. It has to move, right? So the hydrogen does leave, but we leave the electrons there to create that double bond, right? So that might have been a confusing way to say that. So I apologize. But the hydrogen does leave, yes. Okay, so if we are removing, so is E2, is this Zaitsev or anti-Zaitsev? What's the difference between the two? What's the difference between Zaitsev and anti-Zaitsev when it comes to a double bond?
I know that like Markovnikov is less substituted and more substituted. So
Yeah.
I'm thinking it's gonna be around the same like way, I guess. So like
Yes. Yeah.
substituted and substituted.
Yes. Yeah. So what's the difference? So the most substituted double bond is the Zaitsev?
Zaitsev.
Yeah,
Yeah.
Zaitsev. Yeah, exactly. Yes. And so how do we decide how substituted a bond is going to be? A double bond, excuse me. How do we decide how substituted a double bond is going to be?
Maybe with what's attached to the carbons around it.
Yeah, exactly. I'm just redrawing this so it's a little bit more clear. Okay. So, and this is BR. Okay, so this for sure, carbon is going to be in the double bond. So our other two options are here and here. And I say two options because technically these two are the same, right? Is that fair to say that the two orange are the same?
Yeah.
Yeah.
Okay, cool. Okay, awesome. So if we were to have the double bond on the orange, how many substituents would that have?
0.
Okay,
Or 1.
it would have two. It would have two. So we would have one here and one here, which two. I'm writing two because it's. But so if we looked at this maybe from the side, we would have this here, and we would have this here, and then we would have this carbon chain here, right? So the bromine is leaving from this area here, right? So we have, if we're looking at it like this, we have 0 on this side and we have 2 on this side. Does that make sense? So 0 on this side and 2 on this side because this bromine is leaving. Does that make sense?
Yeah.
Okay, cool. So then I'm going to go back and erase some of this stuff. Okay, so we know for sure the orange is going to be 2. And then what about the green? What's the green going to be?
Is it either is it either the highly substituted side or the least substituted side?
Yeah, what I mean is how many substituents would the double bond in green have? How many substituents does it have on this left side here? On this
2.
side. On this side here? This is the double bond itself, so we don't count the double bond.
Oh, 1.
1, yeah, exactly. Okay, so this one has 1. Okay, this side has 1. And how many does it have on this side? Remembering that this will be leaving.
2.
And this one has 2, right? For a total of 3. So our orange has 2 and our green has 3. So if we know that this is going to be Zaitsev, then we do the most substituted. How do we know this is going to be Zaitsev? Has to do with steric hindrance. Do y'all remember? Bulky base. You guys remember OT butyl?
Yeah.
Bulky base. Do you know what OT butyl looks like? Let's see. Let's see if I can draw it out here. Right? And CH3 really looks like this, right? So imagine this molecule in each of these places, right? So it's like this really big bulky thing. So that's why we say bulky base, right? Versus OMe, it's not bulky. So we're not going to have we're not going to have any, like, we're not going to have steric in that same way, right? Is that fair to say? You guys agree? Versus
Yeah.
OMe is just like this, right? So not the same type of steric hindrance. Okay. So we have now deduced that our next portion is going to be like this. Okay. So then next, do you guys recognize this reaction right here?
Yeah.
Kind of, yeah.
Okay. What does that reaction do?
Breaks the double bond.
And does what?
Places a hydrogen in an OH group.
Yeah, we hydrate it, right? We're adding water. So we know that this has to happen at the same time. So we have one is BHF3 and the other is THF. And then we have two, which is OH. And anytime you see peroxide, what does that mean? Now we're at that Markovnikov. We're at the Markovnikov, anti-Markovnikov concept. So what does, and this is across the board, what does hydrogen peroxide mean? What does H2O2, what does that mean you will get for a product? Anti-Markovnikov or Markovnikov?
Markovnikov?
I know, it's such a tongue twister, right?
Yeah.
I love listening to Dr. Gould say it, to be perfectly honest, because he says it so quickly with that accent, and I'm just like, oh, so funny, makes me laugh. But no, so anytime we see peroxide, it's always anti-Markovnikov. So
Okay.
if this reaction is anti-Markovnikov and we are going to be breaking the double bond and adding an alcohol on one side and a hydrogen on the other, where is the alcohol going to go? Is it going to go on carbon number 1 or is it going to go on carbon number 2? What is the difference between Markovnikov and anti-Markovnikov?
It's gonna go on number 1 because
Yeah.
that's anti, and then number 2 would be regular Markovnikov, just because it's more substituted
Yes,
or has more
exactly.
substituents to it.
Yep, exactly. And then I'm not going to draw it, but I'm just going to draw it in a different color that this is assumed. The H is assumed because we're adding O2 across the double bond, right? So, but you can, and it's not wrong. But when we draw line angle structures, we don't typically add the hydrogens. Although there are times when it's helpful to add your hydrogens so you can see where your reactions will be. But in this case, we don't have to. And then what about, does this have any stereochemistry?
No.
Yeah. Why? Or how do you know? How do you know that there's no stereochemistry? The easiest way to kind of tell. Oh, sorry. Go ahead. No, go ahead. Yeah.
Oh no, I was just gonna say because the carbon that the OH is on, it's not a stereo center.
Yeah, chiral center. Yeah, exactly. Yeah. The easiest way for me to tell is like, do I see dashes and bonds? I mean, dashes and wedges, it's like, if I don't see dashes and wedges, there's typically, you're not going to have stereochemistry. That's not always the case, but it's a good way to look at it. But yes, chiral centers are the best way to tell. Perfect. So that's the synthesis, that's forward synthesis, right? Because we were given the reactants. Eventually you'll be given, I think, the reactant and the product, and then you'll have to like do everything in between and figure out what the reactions are. But I don't know, you guys might be there already, but yeah. So, and like, you know, we went through pretty detailed about how to like think about each of these problems. Did some of that stuff help? Did you guys have any like aha moments? Were you like, oh, like that's a good, you know, did you guys have any like questions about how to think about some of those things? We can do
Um,
one more for sure, but I just want to ask about this
yeah,
one.
there were a couple things that I forgot, but as we were going through it, I started to remember and everything. It's just like a
Yeah.
refresher.
Yeah, no, totally. And going back and doing the just like looking at the old, I think she added some like just refresher material for the for OChem 1. Like that's always a good idea, especially if it's been a little while since you've taken OChem 1, to go back and just remember some of that stuff. Um, yeah, any other questions about this particular synthesis before we do one more?
No, I think I'm okay.
So when we're like going through these problems where they're giving us multiple steps with a starting and then we have to get the product, should we think of it as like when we go to the next one, like for example, number 2, like looking if it's a product or an a product solvent just to like get us in the right direction? Would that work every time or just in specific cases?
I mean, pretty much, yeah. We're like basically you're going back through like everything that you've learned, like every single one of these, this reaction, this reaction, right? One, but it's like it's a two-step reaction, right? But those are all things that we've seen in the past. So this we know is just like addition of a bromine through light energy. This one, oh, I'm like, what am I looking at? This one right here, it's some sort of, right, like the last thing we did was substitution or elimination, right? And so one of them made a double bond and the other one made, you know, a leaving group turn into something else essentially, right? With like some other details involved. But you know, that's the overall basis of it, right? So if you don't recognize right away that like, oh, okay, if you see H new, like just, you know, you don't have to worry about like, oh, is this product or a product, right? But when you start seeing stuff like this, then yeah, it's kind of a good idea to think like, okay, is this product or a product? Well, this one's product because, or excuse me, a product because there's no hydrogens. And you know, okay, so that means that it's got to be SN2 or E2. And then, all right, well, what is the, like for me, I like, which means it's concerted, right? So it's gonna, there's no intermediate, so you don't have to worry about that. And then, you know, so it's like, okay, well, what, you know, what number is the carbon? Like, where, you know, what's the, is it a first degree, a second degree, you know? So that I would say for sure is a great way. And then there's other things too where like you'll recognize like this is addition of water, like this 3 and 4 addition of water, right? So that's why I was saying in the beginning how it's like very important to review your mechanisms or review your reactions, review what each of the reactants do and how it interacts with each of the molecules, because that's going to be the best way to be able to like, move forward or move backwards, right? Because eventually we get to retrosynthesis where we've got to say like, okay, we have this product, how do we, I have this product, how do I get to this one? And sometimes there's multiple ways to do it, but we have to be able to do it, you know, forwards first to kind of see how it works with multi-step synthesis. So definitely keep reviewing your reactions. Never stop reviewing your reactions. You know, make like a what are they called? Like flashcards or something, or a Quizlet, right? And
Or
just
like a reagents list or something.
yes, no, literally that reagents list. This is like everything. When you're doing these synthesis, that's what I was saying in the beginning. Like when you're doing these synthesis problems, keep this list next to you. And as soon as you start to get stuck or you start to feel like you don't know what's going on, like just look at it. It's there to help you, you know, because you've got to start building that like you know, that repertoire. You've got to start building that memory, that muscle memory, right? And draw it out, right? Don't like try to do it in your head, although I have done it in my head a few times, but it's, you know, not, you know, it's not easy, right? So it's not really helpful. So just draw it out, because the act of drawing it out will help you as well. Any last questions on this one? We'll do one more.
No, I'm good.
You guys good? Okay. All right, so we'll do this one. I don't know why this isn't uploading. Usually I can add to it from my computer and it'll upload, but it's not for some reason today. Okay, and then this is saying what is the final product? So same thing. And then we have okay, so this is kind of similar to the one we just did, but the good news is that means that you guys should be able to fly through this. So maybe we can do two. Let's find out. Okay. So first, MBS H new. So what are we gonna get?
The bromine addition to the most substituted.
Which is what?
It would be the farthest one on the right, maybe?
This one,
No.
this one. Sorry, this one.
No, I think actually I'm gonna change my answer to the middle.
Okay. This one?
Yeah, but at the top of
This
it.
one?
Yeah.
So
Like,
the
replace
so the
it.
bromine's going to go here, or the bromine's going to go here? One or two?
The same, the two.
Yes. Okay, perfect. Great. Yeah, so we have this stays the same. Then we have this bromine. Oh wait. Sorry. Not replace it. There we go. I'm missing a carbon. There we go. Okay. Yeah. So that's what we have so far. Okay, so next step is T-butyl oxygen. All right. What happens here? Is this protic or aprotic?
Aprotic.
Aprotic, perfect. So what does that mean? Is it concerted or is it carbocation?
Concertic.
Concerted, yes. Okay, awesome. Where will this be interacting? What number or what degree carbon will this be interacting on? First, second, third, allelic?
Second degree or third degree?
This one, yeah, third degree. This is a third degree.
Okay.
Perfect, great job. Technically also a benzoic, but it's third degree, right? So if it's third degree, what does that mean? Substitution or elimination?
Elimination.
Elimination, yes, exactly. Okay, so we'll be eliminating a bromine. And is this going to be Zaitsev or anti-Zaitsev?
Zaitsev.
Zaitsev. So you think it's going to be let me ask you this, is this a bulky base?
Yeah.
So if it's a bulky base, then we have anti-Zaitsev because steric hindrance, right? So that means that a hydrogen, does that make sense? Does that make sense why we're going to have anti-Zaitsev? Okay, cool. So this is one. Will our hydrogen, if we're going to have an anti-Zaitsev, let me change the color. If we're gonna have anti-Zaitsev, what will we have, the green hydrogen or the red hydrogen react?
Red.
So this would be our double bond if it was red, and this would be our double bond if it was green. So if it was red, remember that bromine's leaving. So if this was red, we would have one substituent on this side, and we would have two substituents on this side for a total of 3 substituents, right? And if it was green, we would have a total of, the bromine's leaving, so we would have 2 substituents on this side and 0 substituents on this side for a total of 2 substituents. And we've decided that this is a bulky base, which means it's anti-Zaitsev, which means it's the least substituted double bond. Would our double bond be in the green position or the red position?
Green.
Green, yes. Does that make sense why?
Yes.
Ariel, are you still feeling okay about this?
Yeah. Is it because the bromine is on the it's on that bond?
That is the reason why this carbon for sure will be in the reaction. So it's for sure going to be this carbon, this purple carbon here, because the bromine is our leaving group and it's attached to this carbon. And so when we have elimination, we're going to eliminate bromine, our leaving group, but in this case, bromine, right? And then 1 hydrogen. And so in order to do that, we need to pick a side, right? We either pick this side with this carbon here, or we pick this side with this carbon here. But the process of figuring out what kind of substituted bond it will be is the same, right?
Okay.
So, okay, so now, so what we've done is we've gotten rid of the bromine and we've created a double bond on the green carbon. Okay. And then last but not least, 3 and 4. I'm not going to write it out, but I would suggest writing it out on your exam, right? But 3 and 4, we've done this before, right? We've seen this before. What does 3 and 4 as its own? This is one whole reaction. It's a 2-step reaction. What will this reaction do? What does it do in general? What does this reaction do?
It adds water.
Yes. And how does it add water? Is it Markovnikov or anti-Markovnikov?
Markovnikov.
What did we say about peroxides?
Is that for the anti-Markovnikov?
Yes,
okay.
Always anti-Mark. Anytime you see peroxide, you also, another way that you might see peroxides will be roar, or you'll see like O2, what like this, for example, right? So these are some ways that you would see the peroxide, just so that you recognize them as you move forward. Let me see. I imagine they must be here. No? Oh, right here. This is a peroxide. Oops, sorry. This is a peroxide here. This is your peroxide here, right? So those are some ways that you might see them as well. Okay. So we're adding, it's addition of water across what? Where do we add the water?
The double bond.
Yep, the double bond, exactly. And we decided that if we see peroxide, we know it's going to be anti-Markovnikov. So that means what? Where do we add the alcohol and where do we add the hydrogen? So let's call this A and let's call this B. Where do we add the hydrogen and where do we add the alcohol?
The hydrogen's gonna come off of B and the alcohol is gonna go off of A.
like this. Phenyl just means, right, that's a shorthand. But yes, like this, right? We have the hydrogen that's here, right? So the hydrogen goes here on the B, which is this one. And then the alcohol goes here on the A, which is up here, this one, right? And then what do we think? Stereochemistry?
No stereochemistry.
Yeah. Right? No stereochemistry. Racemic. Perfect. How's that one feel? We whizzed through that one a little bit quicker, right? We got through that one in about half the time, right? How'd that one feel?
Definitely a lot better than the first one.
Yeah, it was about the same for me.
Okay, yeah, no, it's good. Yeah, what is it? Is there like what is it about the or do you feel like you're starting to get some of the cobwebs out? Is there, like how, like talk to me a little bit. Is there like is it just like mostly having to like kind of rinse and repeat, rinse and repeat?
Yeah, basically just knowing not well, kind of like what to do next, but also just knowing where each step goes. You know what I mean?
Totally, yeah, and that comes with practice. That comes with practice for sure. That's why I like doing, at least 15 to 20 problems a day is very important. That's the minimum, right? Like those numbers that I spit out to you, 600 a week. What's that? Let me see. No, I'm sorry, not 600. 60 a week. No, 100 a week, because it's 600 problems divided by, 6 weeks. So that's 100 a week. And then 100 a week, that's 14.28, right? So that's 15 problems a day. That's minimum to get credit for your homework, right? So, really, if you shoot for 25 or 30, that'll really help, kind of move through things a little bit quicker, right? That'll help you to like kind of get those cobwebs out, and you'll be able to see this stuff and say, oh yeah, this goes here, this goes there. Oh, that's anti-Markovnikov, so that means this. Or this is a bulky base, so that means that. Or, oh, I recognize the peroxide. Or, you'll start like the more you work with it. I think people who took OChem a while ago and then are coming back for OChem 2, kind of just working through those cobwebs can be a little bit more challenging than somebody who comes straight from OChem 1. So I feel for you, and, just know that it's still possible. You just might have to put a little bit of work into like remembering,
I have a
Yeah, go ahead.
question.
Yeah.
So when you showed us at the end of your notes those 14 reactions, I was
These
looking
ones?
at, yeah. So are those like the ones that we need to know for this exam? Because I
Yes.
was looking at the other one. There's like for the alkenes, there's like a lot more.
For the
Um,
alkynes?
yeah, for the alkynes, there's a lot more, I guess, reactions there, but I guess we just didn't get to them. I'm trying to find that piece of paper that
These
I,
ones?
yeah, all of those. Do we need to
Yep.
know those too?
Yes.
Okay.
Yes. So the other ones are, oh my goodness, here they are. I put them on the wrong. I'm like, why haven't they showed up yet? It's because I put them at the end of the notes instead of in the middle where I was. Oh my gosh, I'm so sorry, guys. You guys had to deal with my messy handwriting. My handwriting's not that messy in person, but for whatever reason on the iPad, it like looks horrendous. I don't know how. Like when Dr. Pillai does her notes on the iPad, I'm like, how is your handwriting so perfect? Anyway, so essentially the reactions up here are, where are they? The reactions right here should be review, right? So these should all be review, because this is all stuff that we learned last time in OChem 1. So this is all review, like this is addition of bromine. But remember, we try to really use this more like it's just better habit to do NBS HB, because then you don't have, because BR2 can kind of add in all sorts of different ways. So it's a more controlled reaction when you just, if you just get in the habit of writing NBS HB, then you can like actually just get away with what you're trying to do. And then the same thing here with HBr, you know, with some sort of solvent, right? And then HBr roar, right? So that's going to be, so anything HBr is either going to be, it's going to be addition of bromine on a double bond, right? So versus these BR2, so anything like H nu is photobromination, right? So you can add it to just one, you know, not a double bond, an alkane, right? But HBr, that's when you're adding it to an alkene. And so HBr with an inert solvent is going to be Markovnikov versus HBr and ROR, remember, is anti-Markovnikov. BR2 with some sort of inert solvent, that's going to be an anti-addition. And so as you see here, we have a wedge and a dash bromine, right? And then when you have NaOH, that's going to be this, for example, you know, this is a solvent that we see. There's no proton that's involved in the reaction. So that means it's aprotic. So it has to be SN1, I'm sorry, it has to be SN2 or E2. In this case, we're dealing with a allelic carbon, and remember that SN2 prefers allelic carbons, like that's its favorite. And so that's why we see this as an SN2 reaction where we just have a substitution. In this case, these two are both addition of water, right? And one's Markovnikov and one's anti-Markovnikov. When you see the merconium, that's Markovnikov, and when you see peroxide, that's anti-Markovnikov, and we see that here with our most substituted is in the same position. This is our most substituted from this side, right? And as we see, Markovnikov, anti-Markovnikov, right? And then H2 palladium, et cetera, et cetera, et cetera. This is our syn addition of hydrogen across a alkene. And so as we see, we have two dashes. They could also be two wedges, but the fact is that they're the same, right? Syn addition versus anti-addition means that it's attacking from the same side. And then when we go further down, we see this addition of the nitrile group. This is, and as it says, right, your generic SN2 reaction, right? And so this is an allelic carbon. This is an aprotic solvent. It's an allelic carbon, so it's going to be added here on the end. NAT-butyl, this is classic example of your bulky base. OT-butyl, just no bulky base right away. It means elimination, and it's going to be anti-Zaitsev, right? And so that's why we see here, you know, in this case, right, it could go either way. This might be kind of a bad example of that because it could kind of go either way. But yeah, as long as you just pick one, right? And so then we see here that we've now lost the stereochemistry of this phenyl because we've now created, this is now a planar, it's trigonal planar, right? And so that's why it went from a wedge to a line, whereas this one stayed a dash in both cases. Does that make sense? That stuff will matter. So hopefully you guys understand why that happened. And if you don't, we can definitely talk about it. How are you guys feeling about that concept?
Good.
Yeah, I get it. Yeah.
Okay, cool. Okay, awesome. And then let me see, we move on here. We have NaOMe, again, aprotic solvent. This halide is it's third degree, right? So we know that it's not going to be SN2, so it has to be E2, which means that we're making a double bond. And because it's not a bulky base, it's going to be Zaitsev. So we've got this, you know, our two options are 1 or 2, and we have Zaitsev, and we know that we want the most substituted alkene, so that's why we add it here, right? Same thing again here, we have that bulky base, and it's also third degree, right? But so it's not going to react. But anyway, so this is again going to be your anti-Zaitsev. Then we have concentrated H2SO4. That's your E1 reactions. So you're going to see a carbocation. So remember, elimination means that you're going to see a double bond, right? So we're going to eliminate this. This is going to be our leaving group, but we have to make it a good leaving group. And so we add hydrogen to it, right? So we have this is what H2SO4 whoops, looks like, right? And these are all, you guys remember this stuff. And so what ends up happening is this oxygen steals this hydrogen, and then it becomes this over here, which makes it a good leaving group. So then it'll just leave because it's happy to leave, and it'll just be oxygen. It'll just be water, and then we'll have a carbocation right here. But then because we have this carbocation that's not the most stable, we'll have a rearrangement. So then we have this methyl shift, and that's why we see it over here as opposed to right here. And then once that happens, then we have our hydrogen, you know, that makes this double bond here, right? So yeah. So that's that, and then same thing with this, although this is an E2 reaction, right? I don't know why they have this most stable alkene. Yeah, I guess. But yeah, so we have water as a leaving group. So when we see H2SO4 and we have an alcohol, then that means again, same reaction as this. We have to make this a good leaving group. We add an H to it, it leaves on its own. Then we have this is E2 though, so it's not we don't have, this is a concerted reaction, so we don't have well, this one it's not going to happen on because there's I remember I went through all this last time. I made a mistake last time and I put the double bond here, but there's no way because this has 4 substituents already on it. So anyway, what ends up happening is we have the double bond go here, right? Because it has to be, it's the most stable alkene. So what happens is the hydrogen here reacts with it. So, or sorry, the hydrogen here reacts with this to leave to become this, right? So that's all review. Those are all the review from last time. So none of that stuff is new. The only thing that's new for this next exam is going to be this stuff here, which is all these reactions. So these are new ones that we're seeing how to, you know, make or break alkynes, excuse me, how to use alkynes in synthesis.
And then these are all in the notes.
These are all the notes. These ones are on the alkynes, page 18.
Okay.
And I think you guys should get when do the gap notes
I don't know. I thought we would receive one with like all the field notes because I've just been watching the videos.
Yeah, no, I mean, you definitely should watch the videos and fill in your own notes, but I don't think she drops the gap notes until let me see. It doesn't say. When did she publish this? I don't know. Does she not publish them? Does she publish them? It says. Yeah, I don't know. Do you guys not? Have you read the syllabus? Do you guys get to see the gap notes or no?
I have, but I don't remember seeing anything about like the gapped and the filled notes. I don't see anything on the modules either.
Assignments, grading, later missed assignments, communication, email, incomplete policy, threatening accessibility, Title IX, course description. Let me see, modules. What does it have? Course calendar, integrity agreement, pre-test evaluations, how to submittable. Revisiting Oh yeah, first semester organic chemistry review. That might be something good to look at, especially if you're feel like you're trying to figure that stuff out. How to study and prepare for your exam. Jeez. Yeah, I don't know. I don't know if you guys. I don't see it. Again, I've never taken. You can have purchased the electronic version. All it says is that the required material is this, and it can be purchased from the ASU bookstore, or you can get the online version. It doesn't say. Yeah, I don't know.
Maybe
Sorry
she
about
just
that.
wants us to watch the videos and fill in the notes then.
Yeah, yeah. I mean, I'm sure, like definitely that she wants to do that. But wasn't sure if she was also going to release them, but it's not
Yeah, I thought she would too, but I don't know.
looking like it. Yeah, I don't see anywhere on here where it says like it will be released on blah blah blah. Yeah. Oh, I don't know. Yes. Okay, ladies, do you have any other questions?